Scene script. Have you ever wondered how an apple falls from a tree to the ground? Thanks to Sir Isaac Newton, we know it's due to gravity. But what if I told you that's only part of the story? You see, Einstein came along and added another layer to our understanding of gravity. According to his general theory of relativity, any mass, even the apple that fell from the tree, bends space-time. This bending is often referred to as space-time curvature, and it creates a gravitational field. Think of it like a bowling ball on a trampoline. The bowling ball, being heavy, makes a deep dent on the trampoline, pulling anything nearby towards it. Similarly, objects with larger mass, like the Earth, create stronger gravitational fields by bending the space-time around them more intensely. This is why the apple falls to the ground. It's not just that the Earth is pulling on it, the space-time around the Earth is curved, and the apple is simply following that curve. So if gravity is the curvature of space-time, what does it have to do with time itself? Scene script. Imagine you're an astronaut in a spacecraft passing through a region with high gravity. Would you believe me if I told you that your wristwatch is ticking slower than the one your friend has on Earth? This phenomenon, my friends, is what we call time dilation. It's a concept that seems almost fantastical, yet it's solidly rooted in the reality of our universe. Einstein's general theory of relativity tells us that gravity isn't just a force pulling objects together. It's a warping of space and time around mass. In areas where this gravitational field is strong, time begins to slow down. It's like wading through a thick pool of honey, each tick of the clock struggling against the pull. So, in regions of high gravity, your clock, your wristwatch, any measure of time you have, it ticks more slowly than it would in a place with less gravitational pull. But what if we reverse the situation? What happens when gravity is weak or when we move really fast? Now picture yourself in a spacecraft moving at incredibly high speeds, far from any significant sources of gravity. Your wristwatch is now ticking faster than your friends on Earth. This is the concept of time acceleration, a fascinating consequence of Einstein's theory of relativity. It suggests that time can run faster in regions with low gravitational fields and at high speeds. Think of time as a runner on a racetrack. In regions of high gravity, it's like our runner is trudging through thick mud, slowing down with each heavy step. But in areas of low gravity or when moving at high speeds, our runner is sprinting on a smooth, paved track, clocking in faster times with each lap. Just as gravity can slow down time, creating time dilation, it can also speed it up, creating time acceleration. It's a mind-bending concept, isn't it? So time can slow down and speed up depending on gravity and speed, but how does this affect us in our daily lives? Ever used GPS to navigate your way? You might not realize it, but you're experiencing the effects of time dilation and acceleration. Yes, the science that guides us from point A to point B is indeed fascinating. GPS satellites whizzing around the Earth at high speeds and in a weaker gravitational field need to account for these phenomena. The high speed of these satellites causes time to slow down, an effect known as time dilation. On the flip side, the weaker gravitational field away from Earth means time on these satellites is ticking faster, an effect referred to as time acceleration. Both these effects cause the clocks on GPS satellites to differ from those on Earth. Without correcting for these differences, GPS systems wouldn't provide accurate positions. Even a tiny discrepancy of a billionth of a second could throw off your position by almost a foot. So, the science behind your GPS is constantly compensating for these effects of gravity and speed on time. So the next time you use your GPS, remember, you're not just finding your way, you're experiencing the fascinating interplay between gravity and time. From the falling apple to the ticking wristwatch in a spacecraft, gravity and time are intertwined in a cosmic dance. They are the inseparable duo, the lead actors in the grand scheme of the universe. As we've explored, gravity is not just a force pulling objects together, but a curvature of space-time created by mass. This bending of space-time gives rise to an intriguing phenomenon: time dilation. Time, like a slow dancer, takes measured steps in areas of high gravity, making clocks tick slower. Yet in regions of low gravity, or when objects move at high speeds, time picks up the pace, accelerating to keep up. These seemingly abstract concepts have real-world implications, like in our GPS systems, where corrections for time dilation and acceleration are necessary for precise positioning. In the grand theater of the universe, gravity and time play pivotal roles, setting the stage for the cosmic drama that unfolds every second of every day.